Okay, so walk me through how you solve this.
So I multiplied 5 by 180 and I got 900.
Multiplied 5 by 180, how come?
Because that's like that's a factor, so you multiply the AC method, I guess. You multiply the A by C.
How come?
That's like how you solve how you factor.
Not how I factor, or at least that's not the why. I want to know why this works. Why does that work? So I want you to be able to be always very comfortable coming in and being like, hey, this happened. I don't know why it worked. I want to understand why it worked, because I am playing the game of I'm going to teach you why so that it makes sense, so that you could go and explain it to like a 5-year-old. Because if it doesn't make sense, we're not going to remember it and we're never going to care. And it's never going to come up again in life. Like, I want to show you where this comes from. Okay, couple of different things from here. First of all rectangles have a diagonal pattern, meaning any rectangle you give me with dimensions, let's say 2 plus 3 and then 5 plus 4. If you make a rectangle whose dimensions are 5 by 9, which is what this is, and you look at them in quadrants, in regions, this is going to be 10, this is going to be 15, this is going to be 8, and this is going to be 12 square units of size in all those regions. Do we feel good with that so far?
Yeah.
Okay, cool. Take a look at this. What's 5 times 12? Or sorry, 10 times 12?
120.
120, good. What's 8 times 15?
That is 120. 120.
That's weird, right? I didn't start with the same numbers. I didn't get the same numbers in any of the quadrants, but I got the same thing along the diagonal. Do you think that was a happenstance, or do you think there's a hidden truth behind this example?
A hidden truth.
There's a hidden truth, and we can prove it, and we did prove it in class, why this has to be the case for all rectangles. So we're going to use that to help out. So that's fact 1. Fact 2, these are literal tiles. These are sizes of things. This is 5 squares, literal squares, x by x squares. I could go to the hardware store and make them. And then I've got 60 of these x by 1, we can call them rods or blocks. So these are physical things. I've got to organize them in a rectangle. Because do you remember what this is called? What kind of equation is this?
Quadratic.
It's a quadratic. But I only see 3 things here. Why would it be called a quadratic if quad means 4 and I only see 3 things?
Because of the x squared.
It has to do with the fact that they were solved, that they literally represent, they mean, it's in the name, they're rectangle equations. Which is why I always find it a little bit insane that we were all taught to play with them and we were never shown the rectangle. They are literally named rectangle equations. They're quadratic equations. So we're going to use an equation, a rectangle, to organize our tiles. Let's put the x squares in one region for reasons you'll find out when you rewatch the lecture. We're going to put 180 in the diagonal because it shares no common sides. The others were x by x. These are 1 by 1s. There's no commonality there. Okay? I need to take the 60. I need to put the 60 in one of the 2 regions. Like, I could split it up. I could put a little bit more, a little bit less. I don't know exactly how to split it up. We'll come back to that because I'm curious. I don't know what goes where, but I know from my truth of rectangles, there's a diagonal pattern. Tell me, what's the diagonal pattern here? What's 5x squared times 180?
Is it 900 x squared?
900? X squared? Good. So what does that mean I have to get when I multiply along the other diagonal?
900 x squared.
I have to get 900x squared. So I'm looking for 2 numbers, question mark and question mark, that multiply to create 900x squared and that use up my full 60.
So wouldn't that be 30 and 30?
30 and 30. I like that. 30. Well, I use my full 60x. So 30x's and 30x's, right?
Mm-hmm.
Okay, good. I like that. So that means that this is no longer a question mark. This is a 30x and a 30x. Great. Now, this is a rectangle. I can find its dimensions in the same way that I did up here. For example, if I have this 5x squared and this 30x, they both share an x of a common factor. What other common factor do they share?
They're both divisible by 5.
5. They both share a 5. If this is a 5x, how big does this have to be in order for it to be 5x squared?
So like 5x times 180.
If I put 180 here, then 180 times 5x would not get me the 5x squared. What times 5x gets me 5x squared?
Oh, 5x.
5x times 5x would give me 25x squared.
I mean, just x, just x.
Just x. Now, so far, are we feeling legitimately good that for whatever number x is, maybe it's 10, 10 times 5 tens is going to get me 5 10 squares? Like, are we good with like, this is still legitimate and makes sense and feels good?
Yeah.
Good. All right. Find me the common dimension here.
30x.
30x. I don't have an x in the bottom one. Right? There's no 180x. It's just 180.
Oh. And 30?
30. I think 30 works out well, right?
Mm-hmm.
And then what does that mean I have to have for this dimension?
An x.
Okay, let's try it. If I put an x here, x times 5x would get me 30x.
Oh wait, no, 6.
6. Let's try 6. If I put a 6 here, 6 times 5x gets me 30x.
Yeah.
And 6 times 30 gets me 180, right?
Yeah.
So I've got a complete, like I've captured my rectangle in 2 different ways. Let's now take a look at what I've got. I've got 5x squared plus 60x plus 180. That was the inside of my rectangle, right?
Mm-hmm.
That has been described now through us analyzing this in a way that makes sense to us as a rectangle that results from a width of 5x plus 30 and a height of x plus 6. Do we feel good with that?
The width, yeah, the width is 5x plus 30, and then the height is x. Yeah.
X plus 6, right?
Yeah.
And we're trying to figure out when this is equal to 0, right?
Yeah.
In other words, when my rectangle disappears. Well, it's going to disappear in size when one of the sides becomes 0, because then it can't fit anything, right? The inside becomes nothing if one of the sides becomes so skinny that it doesn't exist anymore.
Mm-hmm.
So that means that we're trying to look for either when the width is 0 or when the height is 0, right? Either one of those is going to flatten it to a line, no more area, nothing inside. We feel good?
Mm-hmm.
All right. What's x equal over here?
-6.
-6. And if I plug in -6 over here, we see that the -6 and the 6 would cause that dimension to flatten out. No rectangle. We good?
Yeah.
All right. What about over here?
It would be 5x equals to -30. So
Mhm.
-6 as well.
Also -6. Okay, which we can double check. We plug in -6 times 5 gets us a -30 plus 30, flattens it out, no rectangle.
Mm-hmm.
So what are my solutions?
-6.
-6 and
-6.
and that's it. Very nice. Now, this is why I'm trying to, like, now that we've have this solved, I want us to take a moment. I want us to reflect because I want you to see where I'm coming from and where I'm going to be coming from for the entire semester, okay? Because I'm going to show you a bunch of different things that you've not seen before. I'm just that kind of teacher. It's just how I work, okay? But I do it because I'm motivated by trying to find ways that help everything make sense to you all so that you get the right answer and you know the answer's right and could explain it to somebody else. Do you now see where the error was in what you did the first time? Yeah. So do you remember at the very beginning, you said you needed to take A times C because that's just what the book tells us to do?
Mm-hmm.
Yeah. Now, why did we do A times C?
Like the dimensions of the rectangle.
Well, let's see where A was. This was A, right? That was right here. And then the C was this one right here. That appeared right here. Why did we do 5x squared times 180?
Oh, because that's the area of like each little square.
Each region, each quadrant, sure. And it multiplied to the 900x squared. Why was that useful?
That would be the area of the bigger rectangle.
No, it wasn't the area. It was the diagonal pattern, wasn't it? It was the thing that had to be true with rectangles, right?
Mm-hmm.
So that's where we got it. Once we had that, we used it in the other direction, and a combination of saying rectangles have this property and I only have this much to work with forced us to choose the exact right combination. You see that?
Yeah.
The AC method, if we just take it as I have to multiply things because they're in front of us and the book told us to, it removes an entire beautiful property that you would never have recognized with rectangles because the property, like AC method is horrible. It looks awful. It's difficult to remember. It makes no sense unless we have the rectangle. Then it's like, oh, this has to happen. You kind of see where I'm coming from?
Yeah.
All right. So if you were not in class that day, because this is what we did in class, was a couple of these different examples. If you weren't in class, you've got to go back and rewatch that class. If you were in class and you forgot it, you got to go fill in the guided notes. Whichever way that happened, go and remedy that. But make me a promise right here, right now. You will not do a single thing in math that you don't understand ever again. Instead, you'll come ask me questions and I will help it make sense.
Okay.
Feel good?
Yeah.
All right, I will carry you. You just got to come to me with the questions.